just had an excellent talk by Trac that used to be a postdoc in our corridor a long time ago, and now he's an accomplished senior professor. And I was trying to convey the message that cosmology is getting to a mature state where people might not be needed.
I would argue.
But we will hear more about it in his lunch talk about innovations in computational cosmology. And then after that, he's visiting us, of course, from Carnegie Mellon University. After that, we'll hear from another visitor from Tel Aviv University. His name is Yakov Faerman. He's completing his PhD thesis right now with Amir Stenberg there. And he will talk about hot massive galactic corona. And then we'll hear from Eric Gaidos, who is giving the CFA colloquium. He's visiting us from Hawaii. And he will talk about the bright old sun problem and how to find the ET. I assume that's extraterrestrial. And then finally we'll hear from Rahul Kannan from MIT. We'll talk about quenching, AGN feedback, and anisotropic thermal conduction. Hi, please go ahead.
So in the ITC colloquium, I focused on talking about novel ways to improve data analysis of galaxy clusters for astrophysics and cosmology. What I'm going to talk about today at this lunch is on the other side, how to better model and simulate galaxies and galaxy clusters. So I'm going to talk about innovations in computational astrophysics and cosmology. I'm going to tell you about two interesting projects that are very much a work in progress, but I think the ideas are really powerful. So I'm going to tell you first about a new approach for doing computational astrophysics and cosmology. So if you want to simulate galaxies and clusters, at the very root, you have to do computational fluid dynamics. And traditionally, one of the most powerful methods is to take space, divide it up using a mesh into non-overlapping cells, and then you can compute the flux of conserved variables, mass, momentum, and total energy across these interfaces. And there are well-proven techniques and algorithms over decades of work designed to do this. In particular, this has a lot of success in astrophysics and cosmology. In particular, Lars Hernquist and his group here have been using the Araple code in an unstructured mesh to do this. But constructing a mesh is technically difficult and computationally challenging, and there are times when it doesn't give you ideal solutions. So in around the year 2000, an applied mathematician asked, can I get rid of the mesh? Can I have overlapping cells or particles, but still be able to solve for the flux of conserved variables across interface between particles? And so what they did was they rigorously rederived the conservation equations such that you can have this happen. Okay? Let me tell you first, what you kind of take for granted in the mesh code is that there's a lot of hard work computing the flux across these cells, but you need to make that flux and multiply by this interaction cross-section, which in a mesh code you get for free. You can calculate exactly analytically. When you go to this mesh-free approach, you've gotten rid of the mesh, you've really saved yourself, you've given yourself a lot of freedom, but you don't get something for free. And so now what I've shown here is two particles, I and J, that are interacting. Okay, there's some overlap here. And then there's other nearby particles. So in this finite volume particle method, rather than there being a simple interface area that you can calculate analytically, in general, you have to do a multidimensional integral in this overlap region. And this stalled the method for a good decade because it turns out that calculating this integral, you couldn't do it accurately, and it turned out to be the most computationally demanding step. And then there was a breakthrough in 2011 who said instead of making the kernels for these particles like SPH, where the density varies with distance, since this is an extension of the mesh-based code, let me make these particles have a top hat kernel. And by doing that, instead of doing a multi-dimensional integral, you confine it to a surface instead. And for certain choices, for example, in 2D, if you had a circular top hat, you could calculate this effective cross-section analytically and exactly. And what you have to do is you got to find these different arcs and measure their length, and weight them by the number of particles on either side. This is an exact analytical solution. There's been one case of it being done in 3D by material engineering, where you use cubical top hats because the interactions between colliding cubes are fairly easy to solve. But we already know in computational cosmology that when you have cubes, which are anisotropic, that leads to problems in your solution. So what you really want to do is you want to have, in 3D, spherical top hats that interact. But it's a lot trickier. This has never been solved. When you have two spheres interacting, you cut out a spherical cap, which is easy to base parameterize. But then you're going to have nearby particles that are going to cut that spherical cap into weird geometry. Okay? So this is a problem I'm trying to solve. Already I know how to solve it numerically. Sometimes I work on the CMB. And there we know that when we have spheres, we pixelate it using heel pix. And so you can pixelate these spheres, and when they overlap, you can mark it off through this pixelization. I have a hunch that you can also solve it analytically and exactly, but I think it'll be good to compare both methods. Okay? So I hope that this becomes a really powerful mesh-free approach for doing computational physics, computational astrophysics and cosmology. The code name at the moment is called Ether. These days when businesses are trying to sell you something expensive, they got to give you a cheaper alternative. Okay? So on the other end of the spectrum, while Ether is going to give you very detailed, expensive simulations that really probe astrophysics and cosmology, if you want to compare with large-scale surveys, you need to be able to make fast mock observations, and a lot of them. And one of the ideas that I've been playing with in terms of modeling hydrodynamics without solving for hydrodynamics at all. So this goes back to an idea by my academic uncle, Nick Nedden and Lam Hui back in '98. And what they wanted to do was to take the particle mesh approach for n-body simulations where you have dark matter interacting through gravity, where the acceleration is simply given by solving Poisson's equation. What they realized that if you want to simulate gas dynamics, that you had to have the gravitational term, and then you had to have a pressure force. Okay? And their motivation was they wanted to simulate the low density intergalactic medium to model the Lyman alpha force. And this method works in that case because for the low density IgM, there is a temperature density relation that is approximately a power law. And this is a figure taken from a paper that I worked on with Avi while I was here on characterizing this temperature density relation after hydrogen reionization. And so density is something that you naturally get from a particle mesh code. You can then assign temperatures based on a temperature density relation. You can then calculate a pressure field, take its gradient, get a hydrostatic force, and move particles this way. Okay? But for clusters, I'm interested in the intra-cluster medium. Okay? And it's a lot harder. What I've shown here is pressure on a log scale as a function of relative gas density, also on a log scale. And unlike the IgM, it is not a unique function. Okay? There's roughly a power law dependence, but the amplitude depends on the environment, depends on what's the mass of the dark matter halo that is hosting the intracluster medium. Okay? So a few years ago, I wrote to Nick and I suggested this idea. His initial reaction is always, it's not going to work. And at that time, I didn't really know how I was going to get it to work either. But earlier this summer, I realized that instead of the pressure being just a function of density, you can show that the pressure is a unique function of either the halo mass and position within the halo, or equivalently, the pressure is a unique function of the gas density and the gravitational acceleration. And the gas density and the gravitational acceleration are two things that you naturally get out of a particle mesh code as well, or some higher resolution n-body code. So this was a fun exercise. I had codes that were already working, doing this sort of stuff. And so I put it together over the summer. And it's very close to working. Even though you're not solving for any hydrodynamics, right now I think it needs some fine-tuning, but we're getting temperatures that are differing by about a factor of 2 over a very wide range in mass, from 10 to the 13 to 10 to the 14. And there's some subtle issues that we have to solve, but it's kind of a new intro for a new graduate student of mine. Okay. Thank you. Are you talking about this last? Yes.
You need shocks to build up the pressure, and
So at earlier times, even before the power law temperature density relation is set up, what really heats up the gas is hydrogen reionization. And actually, if you remember, in a series of 4 papers that we wrote a few years ago, we had a model for when we would reionize and the temperature distribution that would come out of it. So actually, this code would do better than just having that simple power law temperature density relation. It would have hydrogen reionization in there. I had a student who just graduated doing work on helium reionization. We could, in principle, put that in as well.
But that's because the heating is done by radiation.
Yeah.
In most the hottest places, it's done by shocks.
Shocks.
And that changes.
Yes. But that's where the ICM pressure profiles comes in. So one of the motivation for this is to be able to systematically put in pressure profiles that form from shocks, that form from, that result from AGN feedback, to put it in directly, systematically vary it, and look for consequences in observables. And that is something that you can't quite do in hydrosimulation. In a hydrosimulation, you vary star formation, you vary feedback, but you can't really control what the ICM pressure profiles would be. Here, you directly control it. You then look for differences between X-ray and SZ, for example, and I think you can do a lot of interesting science that way. So it's definitely a different niche, I think. And in the last few years, there have been a lot of interesting ideas on how to make n-body simulations of, or 2LPT simulations of dark matter faster and be able to probe halos. As far as I know, ever since Nick Netten's work, there really isn't a single case where someone has tried to come up with a fast, approximate way of doing hydrodynamics. And I think it's prime time for that.
In your particle-based meshless code, do you need every point in space to be covered by a particle, and how do you guarantee that that is the case?
It's a good question. So the particles, there's a strict equation that self-consistently describes, as it evolves, how the volume of these particles changes. In calculating this overlap, there are different, in some cases, different supports. So there's a volume for the particle, but for this overlap, you're actually free to choose to make it bigger. And the bigger you make it, you can guarantee that you have interactions with other particles at the expense of degrading your resolution. But that's a good freedom to have when you're in areas that are very asymmetric or elongated. And this is the very problem that's encountered in mesh-based codes. And so that's just why there's an entire class of computational fluid dynamics devoted to these mesh-free approaches to solve some of the problems that are in mesh-based codes. Even in Aeropol, the particles have to be readjusted to make them more centroidal so that they have a regular number of neighbors. Here, and that has to be done in some sense in a global fashion. In this mesh-based code approach, you fix things locally. And I think that's a powerful advantage and freedom. I hope that answers your question.
A two-point question. Is the key difference between this and SPH the fact that these are you solving conservation equations as opposed to equations of motion? And if that is the case, how to handle things like discontinuities and shocks, which has been really the main problem with mesh-free?
So shocks are captured really well when you solve conservation equations. In fact, that's all we really know strictly how to characterize shocks. That's the reason why the basis of this is the finite volume conservative approach. Okay? Some of you may know about Phil Hopkins' gizmo code. That is a similar idea that comes from the other side. So around the same time, an applied mathematician said, can I take SPH, make it more consistent? Consistency in computational fluid dynamics means that if I had a field that was a constant or linear, that I would be able to reproduce it. What was surprising is that SPH can reproduce a constant, cannot even reproduce a linear function exactly all the time. So this applied mathematician set out to make it more consistent by introducing higher derivatives. And he found that at the same time, he could make the equations look like I can solve it in a conservative way, like the mesh-based code. What's unclear to me in reading those papers, and it's very difficult going back and reading applied math papers or math papers, seeing proofs and lemmas and stuff like that, is reading those papers or reading Phil's paper, how do you calculate this effective cross-section between overlapping particles? To me, the most robust way and self-consistent way is that you have to consider the overlap. And in some sense, it would make the two methods identical. From what I've read in the papers, it seems like they simply take the midsection, sometimes just the mid area, sometimes the midsection weighted over some kernel. My suspicion is that it is not entirely self-consistent, but I could be wrong. I know that the first application of this hybrid SPH finite volume in astrophysics, and they actually introduced MHD, they simply took the midsection area, and that surely is wrong. Let me give you put it higher up.
Okay, thanks. Hello, can you hear me? Excellent. Hi, everybody. So in 1956, Lyman Spitzer suggested the existence of a hot gas corona at a temperature of about 1 million Kelvin around the Milky Way. And the theoretical motivation for that structure was a confinement mechanism for gas clouds above the galactic plane. Interestingly, 60 years later today, we have direct evidence of hot gas around both Milky Way and other galaxies in the universe from several different lines of observations, both in the X-ray absorption and emission, and in UV absorption, and from RAM pressure stripping constraints from galaxy satellites around the Milky Way. However, even today, many of the properties of this hot gas are debated or even unknown. Among them, it's the gas density and metallicity, its spatial distribution, and hence its mass. And these properties are very interesting since they can teach us a lot about the formation scenarios of this hot corona around the galaxy or L-star galaxies and its interaction with our galaxy. Is the corona fueling star formation in the Milky Way, or is it the other way around, for example? So in this talk, I would like to present you with the observational evidence for hot gas around galaxies, and then tell you about the model that Emil Sternberg, my advisor, Chris McKee, and I have constructed for this structure, which you can see in this artist's impression from a Chandra press release from 2012. So let's start with the observational evidence. One strong line is X-ray absorption detected through the detection of oxygen 6 and 7. This is oxygen ionized 6 and 7 times. This is 07 and 08, detected in spectra of quasars. And here you can see the distribution of these detections on the sky, excluding the galactic disks. These are pretty much all over the sky. The column densities found in this absorption is rather high, with a few times 10 to the 16 per squared centimeter for the 07, for example. Another line of evidence is from X-ray emission, both in oxygen line and in total band emission in the soft X-ray. And the gas temperature inferred from X-ray absorption and emission is around 2 million Kelvin, pretty hot. So we know there is hot gas out there, but where exactly? So the problem is that the X-ray instrumental resolution doesn't allow us to resolve the lines and the gas kinematics. And so we know that the redshift is consistent with 0, so it's somewhere local. But people debate whether the absorption originates in a local group intergalactic material, in Milky Way circumgalactic material, and some even argue that this is all hot gas confined to the disk of the galaxy. Now, on the local group versus Milky Way scenarios, Feng et al. In 2006 argued that if the corona were megaparsec scaled, then these should have been detected in groups in the local universe, in other groups of galaxies. Since this is not, the hot gas is probably not on a group megaparsec scale. But is it confined to the Milky Way disk, or is it more extended? So here comes the very interesting results of the COS Halos survey. The COS Halos project targets about 40 galaxies, and they look at pairs look at quasars probing the circumgalactic material of galaxies around redshift 0.3, sorry. And what they find is none less than amazing. They find 06 absorption at very large radii from the galaxies of up to 150 kiloparsec. And the column densities are rather high, with a few times, well, 5 times 10 to the 14. Now, these are probing measurements of different galaxies, but they can also be combined into a profile of an average L-star galaxy using normalization by the virial radius. And the last point is that the COS Halos survey finds correlation between the 06 column density and the specific star formation rate in those galaxies. So this is star forming subsample of their galaxies. And interestingly enough, the Milky Way, 06 measurements in the Milky Way are consistent with the COS Halos measurements. So following these observational evidence, these data, I'd like to present our model. We aim to construct a unified model combining X-ray and UV data, and it's universal in the sense it combines data from the Milky Way and other L-star galaxies in the sort of local universe. At first, our model is phenomenological and analytical, aiming to reproduce as much as possible of the observational data. And one of the results will be that it produces a massive corona with a significant mass of hot gas. Our first assumptions are that the oxygen ions are produced in extended structure, extending out to the virial radius of the Milky Way at about 250 kiloparsec. We assume that the gas is in hydrostatic equilibrium and spherical symmetry, and that the ions are in ionization equilibrium. The ingredients of the model are, on small scales, we assume that the gas is turbulent, following numerical simulations of plasma gas, and hence it has a log normal distribution in gas density and temperature. The fluctuations are isobaric, so the high temperatures correspond to lower densities and vice versa. Our model is two-phased. The first component is hot gas, which is matter accreted from the IgM, falling onto the galaxy and being shock heated to the virial temperature at about 1 or 2 million Kelvin for the Milky Way. But the high-end density of this tail cools rapidly and forms the warm component in which the O6 can form. So this is the small fraction in the warm component. So on small scales, as I said, the gas is turbulent, but on large scales, we assume that the gas is in hydrostatic equilibrium. This is something that's seen in the illustrious simulation, for example, where the gas flows past the virial shock and then slows down and settles to form a quasi-static corona. We allow for thermal support, turbulence support, and some support from magnetic fields and cosmic rays. Since the warm gas in our model is mixed with the hot phase out of which it condenses and cools, it naturally forms an extended profile as seen by the Cos-Halos observations. Finally, I'd like to present parameters of a fiducial model within the framework that we have constructed. The gas temperatures of the hot and warm components are 1.5 million Kelvin and 300,000 for the warm component, which you can see here. Coincidentally, this has been the temperatures in Tel Aviv last summer during the day and night, so maybe you shouldn't visit in August. Our model successfully reproduces the O6 measurements of the Cos-Halos survey, so markers are the measurements, and the black line here is our model. And we also produce significant columns of O7 and O8 with a metallicity of 0.5 solar, so this is enriched gas. The density profile of the hot component is extended with about 10 to minus 4 particles per cubic centimeter at around 100 kiloparsec, consistent with REM pressure stripping constraints from Milky Way dwarf satellites. And since the density profile is extended, the total gas mass is high with slightly above 10 to the 11 solar masses. Together with the galactic disk, this is capable of closing the galactic baryonic budget for a Milky Way-sized galaxy. And most of the gas is in the hot component, with about 20% in mass in the warm component. Last, I would like to show the emission properties of the gas, which we calculate. So first, we can use the cooling functions to estimate the lifetime of each component, and we find that while the hot gas has a long lifetime of about 10 gigayears, the warm gas, sitting at the top of the cooling function, has a much shorter lifetime of about 100 megayears, so it needs a constant energy input, for example, from stellar or AGN feedback, which is something that's also suggested by the Cos-Halos correlation with specific star formation rate. And last, we calculate or predict the detailed emission spectrum of the corona. This can be used to predict or compare to observations of soft X-ray emission in this 0.4 to 2 keV band, and for comparing to observations of oxygen line emission. I'll just finish by putting my summary and saying thank you. Right. So I'm not sure how this could be tested observationally. I mean, the scenarios of heating from below or radiation from below rather from above.
The ionization structure would be quite different if it's coming from below versus above. So you will have an ionized layer of the galactic H just above the galactic H1.
Right. So. Right, so I'm not familiar with these kind of observations. One thing that we are doing now is comparing the emission from the corona with the intensity of the metagalactic radiation, which we can then appreciate if this is significant for that, for example.
Yeah, this 3 times 10 to the 5 Kelvin, right in the middle of that cooling function, should be violently unstable, right? Thermally unstable.
Right.
So why is the gas sitting there? Why doesn't it come down to 10 to the 4th?
So that's a very good question. So I guess I can try to answer this from 2 directions. One is that we see O6 around galaxies, and O6 has a very peak in temperature for the ionization fraction. So we know it traces gas at around 300,000 Kelvin. It's out there. So I agree that it needs an energy input to survive there, at least for some time. And that's a good question of what supplies that energy. In terms of thermal instabilities, there are simulations of turbulent gas, of gas clouds condensing out of a hot medium. And these simulations, as far as I'm familiar with, show that while clouds start to fall on, for example, onto the galaxy, they're then disrupted very quickly and they're mixed back into the hot ambient medium. So in that sense, there is a cycle, and they don't necessarily fall all the way onto the galaxy at a huge accretion rate.
I just had a comment. Are you focusing mostly on the spirals? Because in X-rays we see many hot coronae around early hot galaxies, just a few around the spirals. There are a couple papers by Bogon and by Anderson where we see around massive spirals.
Right.
Corona emission.
So we're focusing on spirals on star-forming galaxies since we're using both the O6 and the X-ray data. So in that sense, I think this is a picture that's consistent since the hot component is long-lived and can survive even after the star formation ceases. So I'm familiar with X-ray observations around massive spirals. I know that the sensitivity in the X-ray is challenging to observe, I think, this kind of emission around lower mass galaxies. And the density is very low, yes.
So you do see it around the bulge of M31.
I'm sorry?
You see wind in M31.
Okay.
There's a wind detector coming out of the bulge.
Okay.
Really quick, so your model depends on different parameters like pressure support from cosmic rays, magnetic fields, turbulence. Are you able to apply your model then to observations, like cross observations or oxygen 6 lines, and then take those parameters back out so we can start trying to make estimates of those in the CGM?
So that's an interesting question. I think in the O6 data, they definitely see that the lines, so in the UV, the lines are resolved as opposed to the X-ray. And for the COS data, they definitely see that the lines are wider or broader than their thermal width, right? So I think that's evidence for the turbulence is present and significant. And in fact, in our model, the turbulence is at this point an input parameter. So, but maybe in the future we would like to combine this more turbulence physics to try and maybe predict some structure of the lines or kinematics. That can be interesting.
Thank you very much,
Right. Sorry. Thanks.
Okay, can everybody hear me? I'm on? Okay, great. So I want to thank Avi and Anastasia for inviting me to quickly tell you about something completely different now, before you get back to more traditional astrophysics. I'm Eric Gaidos. I'm visiting and giving the colloquium this afternoon. And mostly what I do is work on very low temperature particle physics. That is, planets, very big particles. But I share an interest with Avi in the distribution and evolution of life in the universe, the possibility of it. And working on exoplanets and how to detect them has brought me along some strange paths. This is one of them. And so I'll just kind of introduce this idea. It's kind of fun, and see what you think. It's based on something which I'm sure almost everybody in this room is very familiar with, and that is stellar evolution. We have the faint young sun paradox regarding our climate. We also have a bright old sun problem. This is a laser pointer, yes. Yeah, I got it. Thanks. So what you see here are basically two tracks here, one for a G dwarf, one for my favorite type of star, the M dwarf. The M dwarf does not have this problem, but we who are orbiting around a G dwarf definitely do have this problem, and that is that the irradiation from the host star, the G dwarf, is going to rise rather precipitously as the star approaches the end of the main sequence. The faint young sun paradox, which is an outstanding unsolved problem in climate science, is on the order of this scale here, sort of a 30 to 35% problem. You can see that what happens to the climate of the Earth in the future is of a 1 or 2 order magnitude larger, and dwarfs, both of those dwarf the effect that everybody's concerned about today, rightly so, which is anthropogenic climate forcing, which is on the order of 1% in this diagram. So basically something a little thinner than the thickness of these individual lines. But nevertheless, that 1% can make a big difference, as we are starting to appreciate, especially at northerly latitudes. And so people, including physicists and very good astronomers like Roger Angel, have given some thought to what we might have to do if we don't behave ourselves and control our carbon consumption habit. And one of those is to actually modulate the irradiance that's coming to the top of the atmosphere by the use of what is called a sunshade or a star shade. And you can conveniently place this at an L1 point, which is not a stable point, but which is sort of neutrally stable and thus requires minimum dynamical maintenance in order to keep something between you and the sun. So you place something there to block out part of the sunlight. This is an engineering project, of course, on a massive scale. And Roger, who is a brilliant optical engineer, basically tried to figure out ways you could try to minimize the cost, that is, the mass you have to send to the L1 point to do this. It's big. It's trillions. But of course, you know, we talk about trillions of dollars now in terms of other expenditures of our national budgets, which are somewhat less worthwhile than, say, saving the planet. If we had to do this, we could, is what Roger claimed to do. And I'm not going to disagree with him, at least on the optical science part. And there are a couple of different approaches you can use as to what you place there in front of the sun. What Roger came to the conclusion is that in order to get optical interference, basically destructive interference of light over a broad wavelength range, which is what you want to do, not to have something opaque which would heat up, but to have something that would basically destructively scatter the light away from the Earth, you would require a very clever arrangement of thin films that were basically inducing the destructive interference over this wavelength range of interest. So this is engineering, optical engineering on a fine scale, very subtle. A sort of more brute force way is to use a size, mass, radius relationship that favors very small particles having a large surface area per mass, and thus we would go to very small scales like dust. And so you would basically produce dust clouds at the L1 point, which would block some of the sun. And you might place some mass source there to serve as a source of the dust. The dust, of course, is not stable there. Due to Poynting-Robertson drag, you would actually place the source at a modified place closer to the sun to account for the effect of the radiation pressure, but nevertheless you would have to have basically a constant supply. But an asteroid over some time scale of interest might do it. So these are of course, fantastic things that hopefully we'll never have to engage in for our sake as well as the planet's, because I don't think we can trust ourselves that well. But if we wanted to do this, we could. Okay? And of course, there is this other problem out there that eventually somebody's going to have to do something about this. Okay? In the future, not our problem, but millions or on this time scale, billions of years from now, if, for example, you were so altruistic, say, in some grand scale, to want to preserve the planet for much longer, to let the life forms that are still there persist against what will inevitably happen there, a runaway greenhouse in an inhospitable climate state like Venus, then you might want to do something about it. So this is just another diagram showing the geometry. I'll just skip this through. And this tells you some of the scale of the problem then if you want to do this on the big scale of attenuation. So we're no longer talking about 1% effects. We are talking about having to attenuate at the 20, 50% or more level, and what the optimal size of the star shade you would require to do it. It turns out that basically that star shade is about the same scale as the planet if the planet's a planet the size of the Earth around a star like the Sun. This happens to be a coincidence. Maybe slightly larger, but essentially you want to have a star shade that is about that size. And if we wanted to be clever about this, of course, we have to take into account of the long time scale that the Sun is going to evolve, or your host star is going to evolve and get larger, and the surface temperature, the effective temperature will change. And so you may want to have a clever arrangement of that dust cloud or that cloud of particles or scatters, that as the Sun grows, which is what the red circle is doing here, that you're basically incorporating more of the scattering particles, and thus you can sort of automatically or passively compensate for stellar evolution. So instead of the irradiance going up like this over time as your star ages, you could basically modify it that without doing anything else, you could almost flatten it out passively. But of course, you could consider something that is a little bit more active and responsive, but there are geometries that are more clever than others. So we haven't done this, and what comes after us in 1 billion years from now or half a billion years from now, it's hard to say. But of course, in the big scale scheme, we can ask the question, has somebody done this? Or something done this? An agency out there around another star that has decided for whatever reason that it wants to modulate the climate of the planet that was, say, originally in the habitable zone, or could be placed back into the habitable zone by an appropriate modification of the incident flux. And then the other question, of course, is could we see this if indeed this has happened? And this is where consideration of transiting exoplanets has sort of led me a little down this detour. Of course, star shade will be, at the L1 point, will be occulted by the planet, but the occultation is not 100%, because as the planet passes in front of the star during a transit, which is what our favorite technique, or one of our favorite techniques for planet detection is right now, the star shade will also pass, but not at exactly the same geometry. So there will be occultation of the star shade of the star, but there will be also occultation of the planet by the star shade, which will change during the transit event, which will produce a somewhat non-canonical light curve. And these are some calculations to show what the shape of that transiting light curve. A traditional transit light curve looks like this, the planet passing from the star, very close to that. But as you view the star shades on a geometry which is on a chord or impact parameter which is close to 0, you get a little increase here in the middle of the transit. And this is small. This is parts per million. But with a super Kepler telescope, or perhaps with a Kepler-like telescope and around a very bright star where the signal to noise is very high, this is conceivably detectable. And these are sort of the star shades of the size that you would need in order to compensate, say, for evolution into a subgiant in the case of a solar mass star. If the agency were to choose to use dust clouds, particles, of course, these scatter in a very particular way, such as me scattering. So for single scattering events, you can calculate this fairly relatively easily. You get a bump here, but you also get an increase on either side of the transit, ingress or egress, which is capable of, possibly detectable. This is a very small effect. So very quickly, the kinds of stars you might look around are obviously not M dwarfs, which don't have this problem of stellar evolution, but higher mass stars. And you can look for the associated star shades associated with planets that are either just inside the habitable zone or perhaps are slowly evolving into the outside or interior to the habitable zone, either mitigation efforts or rescue efforts that is plucking a planet back into the habitable zone from some Venus-like climate state. And then you have to worry about the details of this. There are effects out there which produce non-canonical light curves, like star spots, and you have to worry about this. But one thing is important is that this event or this structure would have to be persistent. So star spots come and go, but a structure that was presumably something that lasted 500 million years presumably won't go away in just a few months or a few years of monitoring. And I'll end there. And if you have any questions or ideas, I'll take them. Thank you.
Eric, this is very inspirational. The one question is, there will be another signature of the same culture, which is it will re-emit the radiation that it blocks or scatters, and there would be at a different temperature than the planet. So if you were to detect the thermal emission from that you expect the planet is, you would get a component that is not consistent with this.
Right. Yeah, so in fact, that's sort of was my first line of thinking. And I have to credit my colleague Ray Purenbert, who sort of pushed me down that path. And he said, could you detect what you just described? The issue is that you have to know the albedo of the planet fairly exquisitely, well, precisely, in order to disambiguate those effects. But that is, in fact, modification of the equilibrium temperature of the planet, if I understood what, yeah. That is another alternative way. But you have to know the albedo then in order to get that right. So you have to have a direct, that's harder right now for us than the transit method.
And there is this stubby star that people are talking about.
Oh, yes.
Stars seem to fade away.
Yes.
Do you think it, what is your interpretation of that star?
Oh, I thought the canonical interpretation is aliens. No, sorry. No, sorry. You know, I don't know. What I can tell you is that I and a graduate student, Megan Ansdell, at the University of Hawaii, we work on these Dipper stars, which are very similar in the shapes of the light curves. There's some differences. They show these rapid dimming events. And what distinguishes those stars from tabby stars, as it's called, is that they all have disks around them. And so we can safely assume it has something to do with the circumstellar material. Tabby star does not show any evidence for a disk. There is this long-term dimming, which is suggestive there is something obscuring the star partially. You also have to remember that we've looked at the star with some imaging, but I'm not sure we know all the details of the neighborhood of that star. It's possible there is another star there, for example, that could be producing this signal. And Kepler just sees everything superposed. So, oh, yeah, sorry.
In the old age sun problem, in addition to worrying about the change in temperature, you have to worry about change in harmful particles from solar winds or cosmic rays?
Well, of course, the sun's rotation is slowing, so if the magnetic activity drops according to that, then the prediction is that the sun will become less active over time. And so you can look at that as a two-edged sword. Particles, if you are exposed to them in the vacuum of space, are extremely harmful. Of course, you have an atmosphere above you. They also could modify the chemistry of the planet's atmosphere. And that might be a good thing, for example, if you don't want to live under a thick hydrogen atmosphere. So a planet which is under 100 bars of hydrogen might not be the best place for an oxygen-respiring organism to evolve. So you might have to get rid of that first. So activity might be a good thing.
And of course, there is the notion that if your civilization is advanced enough, then
So presumably, an agency which could do this readily without even too much effort would probably not be worried too much about the climate state of the particular planet because they wouldn't need it. They could just live in domes or on computers. I mean, you have to think about the long run. Think about a million years ago what people would have thought of the technology that we're using today, and then multiply that by 10 or 100 or 1,000. I think, you know, from our perspective, which is can't count for anything compared to a billion years from now, it would be perhaps the sense of when we look at a national park and we want to preserve it. We see something beautiful there, and we want to keep it the way it is. And so perhaps an agency would look at their home world or some other world and say, you know, this is where life is doing some wonderful things, and we'd just like to have it keep on doing that for a little while longer.
Thank you very much.
Sure. Now back to your regular programming.
Hello, so my name is Rahul Kannan, and I'm a postdoc at MIT, working with Mark Vogelsberger, and today I'll talk about quenching, AGN feedback, and anisotropic thermal conduction, which I'll classify as non-traditional, traditional astrophysics. So, let's directly jump into it. So clusters are the largest objects found. They contain a large amount of hot, that's just 10 power 7 to 10 power 8 Kelvin gas, and it's usually very low density. It's called the intracluster medium. The reason it is important is because at these low densities and high temperatures, non-traditional astrophysics processes like magnetic fields and anisotropic thermal conduction start to become important. Especially in clusters, the conduction time scale, if you calculate the conduction time scale, it's much, much smaller than the dynamical time scale. And so conduction starts to become important. And the anisotropy in thermal conduction arises from the fact that the gyro radius of the electron in ICM conditions is 12 orders of magnitude lower than the mean free path of the electron along magnetic field lines. And so you only conduct along magnetic field lines, and across magnetic field lines there is zero conduction. That's the anisotropic part. And so in order to simulate all these processes, you need efficient magnetohydrodynamics and a thermal conduction scheme. And you also need high resolution in order to resolve the ICM and not just the central galaxy. So we are doing just that. It's called the ASTUS project. We use extremely high resolution simulations of a 6.5 times 10 power 14 solar mass cluster. And the aim is to resolve and simulate all the relevant ICM physics that goes on using our EPER. And I note that this simulation is has a 1,000 times better mass resolution and 30 times better spatial resolution than any previous simulation with conduction. And it also includes all the relevant galaxy formation processes like star formation, AGN feedback, and metal deposition, etc. So let's get into the results directly. So I simulate the cluster with two different physics. The blue line, the no-con run, has no conduction whatsoever, so it's pure hydro plus MHD, whereas the red line is MHD plus anisotropic thermal conduction. And I show the temperature, density, and the entropy profiles at redshift, three representative redshifts of 1.4, 0.7, and 0.35. And as you can see in the conduction run, you actually convert the cluster from a cool core to non-cool core to cool core much earlier than in the non-conduction run. And also, if you look at the star formation rates, which are the solid lines here, you have very low star formation rates, especially below redshift 1.5 in the conduction run, whereas in the non-conduction run, you have star formation rates of over 200 solar masses per year, even at redshift 0.5 or so. What this does is it also changes the color of the central galaxy, for example. So I plot the G minus R color, which is the dashed line here. And for the non-conduction run, due to the high star formation rate, you take the galaxy into the blue sequence, whereas the conduction run maintains its redness. So I show that here, for example, this is the no conduction central galaxy in the no conduction run. It's blue and star forming at redshift 0.5, whereas in the conduction run it is red and non-star forming. Okay, so you can say, so you can ask, what does conduction do, or why is it quenching stuff easier and faster, and why is it converting a cool core into a non-cool core much earlier? Now, if it's just conductive heating, then conductive heating can only make the temperature profile isothermal. It cannot invert the temperature profile, right? And also, even in the non-cool core phase, where the temperature gradient is outwards, the heat should actually go outwards. It should not go inwards. So you cannot conductively heat. You rather conductively cool. But you are actually quenching more in the non-cool core phase. So what is happening here? It's definitely not conductive heating, right? So in order to understand what is happening, we also look at this does not show properly. We also look at the metallicity profiles. So at 3 different redshifts, at redshift 0.35, 0.18, and 0. So you start with a central metallicity core, which is formed due to star formation, right? And then usually metals are distributed through AGN outflows or star formation. But at redshift 0.35, there is no star formation, though it's basically AGN outflows. But in the non-conduction run, the core remains, even at redshift 0. Whereas in the conduction run, the core is smaller, but then the core gets mixed out totally, right? And the question is, what does conduction do to metals? Because metals should not be affected by conduction. It should only diffuse heat and not metals. So you're actually seeing more mixing in the conduction run, and which is an important clue as to what is going on here. You can also quantify the metallicity map. So you can plot the metallicity as a function of radius at the same redshifts, right? You have a strong core to begin with, metallicity core to begin with in both the runs. The core in the conduction run is smaller because there's less star formation, of course. But by the time you reach redshift 0, the core is completely erased in the conduction run, whereas in the non-conduction run, the core remains. And you also see the dispersion decreasing, the metallicity dispersion decreasing as a function of time. This is conclusive proof of metal mixing, right? And if you want to look at observations, I overplot the observational estimates of the metallicities of clusters here, and you see that the conduction run matches the metallicity profiles much better than the non-conduction run. You don't see this extremely high metallicity core in observations of those. So this basically indicates efficient mixing in the conduction run. So you can say that the AGN, you can say, yeah, you induce mixing by injecting AGN jets and winds, but that is not the case. So again, here there's the cumulative amount of AGN energy injected into the ICM. The blue line is the non-conduction run, the red line is the conduction run. And you can see that the amount of energy injected by the AGN is lower in the conduction run. But the quenching is much more efficient. Cool core to non-cool core transition is much faster. Metal mixing is much more efficient. All this is happening even though you are injecting less amount of AGN energy into the ICM. So what is happening here? In order to understand that, you have to understand how the AGN actually interacts with the ICM. So if you do pure hydrodynamical simulations of AGN jets interacting with the ICM, then you'll find that the AGN jets are extremely inefficient in coupling their heat and energy into the ICM, because they just form low density channels through which most of the energy escapes, and they deposit most of it into the outskirts of the ICM rather than into the cluster core, where it is important in order to stop star formation. So what conduction does is it's a bit complicated here. So the point is that the dynamics of a rapidly conducting plasma, that the conduction timescale is much smaller than the dynamical timescale, is very different from a pure hydrodynamic plasma. Under these conditions, the gas is isothermal along magnetic field lines. So what you can do, so if you have a pure hydroplasma, then if your entropy gradient is increasing as a function of radius, entropy is increasing as a function of radius, then your system is stable to convection, right? But that is not the case when you have anisotropic conduction. I'll show here, for example, you have something called a heat flux driven buoyancy instability. So even if your entropy is increasing, if your temperature is decreasing, even if you perturb it a little bit, so you're perturbated with a Mach number of 10⁻⁴, the system goes unstable and kind of saturates. Okay, and the other case is dTdr is less than 0. This is the non-cool core phase. Here, it's called the magnetothermal instability. And even, again, you put in a small velocity perturbation of 10 power minus, Mach number of 10 power minus 4. And as you can see, it forms this Rayleigh-Taylor instability pretty fast and induces convection, a rapid convection in the ICM. So the main takeaway point of this is that the entire cluster ICM is convectively unstable, no matter what the entropy gradient is, what the temperature gradient is. It's always unstable if you have anisotropic thermal conduction. Okay, and you saw previously that you have these instabilities kind of saturating after a certain point. But even if the instability saturates, the restoring buoyancy forces in the saturated state. So if you have a stratified plasma, and if you perturb this plasma adiabatically, then the restoring buoyancy force is judged by the entropy gradient of the plasma. Whereas if you have anisotropically conducting plasma in the saturated state of these instabilities, then it is given by the temperature gradient. Okay, and if you calculate FTC and FDB in our simulations, you see that FTC is always less than FADB, which means that your restoring buoyancy forces, even when in the saturated state, are much, much lower than the restoring buoyancy forces in a pure hydroplasma. Okay, this means you need less external turbulent energy in order to induce mixing. And this can lead to efficient isotropization of the injected AGN energy. So even if you have a small amount of turbulence, what it can do is, if you have a small amount of turbulence in a purely hydroplasma, it kind of oscillates around that point with the Brunt-Vasala frequency. But if you have the less small amount of turbulence in the conducting plasma, then it can automatically induce mixing. Okay, and this is why you see metal mixing, heat mixing, and that's why you see much more efficient quenching and much better coupling of the AGN with the ICM and the cluster core. So the conclusions: anisotropic conduction makes the entire ICM unstable and prone to mixing. Even in the saturated state, the less external turbulence is required to induce mixing, and leads to efficient isotropization of the energy and making the quenching more efficient. So if you really want to do cluster physics properly, you need to include anisotropic thermal conduction. Thank you. Oh, thank you. Yeah. Yes. So, yes, exactly. So it even reduces the thermal instabilities that you get by just so if you have like AGN shocks in the cluster core, it just mixes the hot and the cold, and then you get like a warm plasma, which takes a lot more time to cool rather than the normal hydrodynamic plasma. So that's what you see here. If you have pure hydroplasma, you have AGN just forming jets here, and this is all high density, really cold gas, but that's not what you see when you have. If you can mix this hot gas with this cold gas, you couple things much better.
This is really, really interesting. The thermal conduction in the MHD depends also strongly on the alphane Mach number.
Yeah.
So what was the alphane Mach number in this run, and are you planning to do other runs with different strengths of the mean magnetic field?
So the mean magnetic field here is given, is self-consistently calculated here. So you have like a primordial magnetic field of 10 power minus 14 Gauss, and then you have dynamos, turbulent dynamos within the simulation, so the magnetic field is self-consistently calculated. So if you really want to do this, then you have to do non-cosmological simulations in order to understand what the magnetic field does. Yes, I'm trying to do that now. It can also suppress some of these instabilities, but that's not what we see, at least in cosmological simulations. Here, at least, we see efficient mixing. And I haven't really checked.
It would be interesting then to check what the alphane Mach numbers are.
Yes, in these simulations, yes. I haven't done that.
Agrees with the theoretical predictions or not.
Yeah, we should definitely talk. Yeah, sure.
Any other comments? Not, let's thank Rahul. Please gather outside. We do once a year.
Oh, thank Thank you so much for
The
inviting.
mic
Oh, yeah.
current. Switch.